Here we're asked to solve a first order linear differential equation given by x squared y prime plus xy equals 1, and we're told that x is greater than or 0. So to solve this, the first thing we need to do is get it into standard form. So in standard form looks like y prime plus 1 over x y is equal to 1 over x squared. And of course we're allowed to divide everything by x squared because as long as we're restricting ourselves to x being greater than 0, we are never dividing by 0. So this is totally okay to do. And now we have it into standard form, so we can identify what our p of x is. P of x is 1 over x, and here our q of x is 1 over x squared. So to find the integrating factor, what we can do is first we would like to integrate p of x with respect to x, and that is the integral of 1 over x dx, and of course that is ln of the absolute value of x. But because we know that x is always positive, we can then just simplify that to ln x. We can get rid of the absolute values, and so therefore our integrating factor I of x is equal to e to what we found when we did this integration, which is ln x, and of course that simplifies to just x. So multiplying our differential equation by our differential equation in standard form, which I guess I might want to label maybe equation 1, we're going to multiply equation 1 by our integrating factor. So x times equation 1 gives us x y prime plus y is equal to 1 over x. We can now see that the left hand side is actually a product rule. So this is actually equal to x times y, and the derivative of x times y. At this stage, you should probably convince yourself that indeed when you do this derivative, the derivative of x times y, you do recover the left hand side of this equation, and in fact you do. So now to get rid of this derivative, we can take the integration. We're going to integrate both sides with respect to x. That leaves us with xy is equal to the integral of 1 over x dx, and of course that is again ln of the absolute value of x plus a constant. But because we are restricting ourselves again to situations where x is greater than 0, we can just rewrite this as ln x plus c. And now that we have it in this form, we can rearrange it into an explicit form. So y of x, just by dividing everything by x, y of x is equal to ln x over x plus c over x. So one thing I want to point out about this is if we had not restricted ourselves to x being greater than 0, of course we would have to deal with the absolute values a little bit differently. But more importantly, x would be a singular point. X would be something where if we divided by x squared, we would end up with dividing by 0 possibly. So if we didn't do this restriction and we just carried out this solution, what we would find is our solution is actually not continuous at x. There's obviously some problems at x equals 0 for our solution. So I just want to point out that if we had not restricted ourselves to x being greater than 0, we would have a singular point at x equals 0, and of course that actually does carry through into our solution, that our solution would not be defined at x equals 0 either. So you do have to watch out for this whenever you are encountering singular points.